Okay, with the equations of motion and the collision transform relationship, the next step is you just need to simulate the bipedal walking. So for a certain time interval, okay, for the given initial conditions for theta dot, phi dot, your code is going to be composed of maybe three sessions. With one thing is like a main function, main and file, defining all the parameters and initial values. And maybe you could do the for loop, repeatedly calculating the Poincare section and see if those values will converge to a fixed point. Okay. So depending on your preference, maybe you can define the Poincare section as the initial onset of every swing phase initiation after collision as your Poincare section, or maybe you can define the apex like a apex point where the center of mass is the highest point as your Poincare section. It really depends how you choose. So your F1 step is a function that calculates the Poincare section. And after each, you return to the main function, like after you calculate them, you just update your initial value and then you just keep store those calculated value and see if this converges to a certain fixed point. Now, your F1 step is composed by what? The two steps. One is to calculate the equations of motion integral, and the other is handling the collision problem, right? So after equations of motion solving, you actually solve up to collision occurs. So events should be turned on, and you have to solve the FEOM for theta and phi. Okay, two parameters, and then for once you have an event that means collision occurs, your final value for the time and the state variable x indicates before collision parameters. So using the relationship, what we have just worked on in the previous video, you can calculate what's going to be the after collision state variable. And then by doing that calculation, you can actually return your new the parameters at the Poincare section to your main function. Okay, so how your equations of motion function look like? Your equations of motion are pretty much based on your equations of motion. Okay, so you're calculating the acceleration term. And whenever there is a event occurs, okay, you have these three steps. Okay, first you should find if your event indicator crosses zero. Your event indicator is actually the relationship between the two theta and the phi. If you have a 2 theta equals to phi, that's the time that the collision occurs. So your 2 theta minus phi is equals to the collision indicator, and then when this one equals to zero, then event occurs. And what will happen? Like, what are you gonna do for when event occurs? Are you gonna stop? Yes, but note that whenever, as I noted before, those condition, like those 2 theta is gonna be phi kind of condition can happen during the swing, okay, during the swing. So you should actually define certain constraints that if this value is greater than that, then the collision occurs. Otherwise, just it's just happen when your swing leg crosses the stance leg. Okay, finally, how about the slope? Is the slope matters? Yes, because your swing leg is actually moving forward and back, and that's where collision occurs. So usually phi is greater than theta, so minus slope, negative slope matters. So at this event occurs, then means collisions. So you stop integrating equations of motion and toss your calculated value to the collision calculation part. Okay. If there is no event occur, your output is just simply the same as equations of motion based calculation for the acceleration. Okay, so this is a sample for simulation. What do you see? This seems like unstable, failed to find the repeated limit cycle. Okay, so your stance leg depicted as a blue line and swing leg as a green line just keep repeated, but not at the same value, not converging, right? So how to find a limit cycle? Well, for this, try and errors. Just you try different initial condition and until you find one. Okay. So luckily, I found the limit cycle. So as you could see, there's a swing leg has been switched here at the collision to the stance leg, and the stance leg here has been switched to the swing leg, and it seems like it's repeating. Okay. And note that if you're looking at the velocity term here, the theta dot, phi dot, and psi dot, and the theta dot, as you can see here, there is a discontinuity. Okay, so your angular velocity has been reduced after collision. This is collision loss. Okay. Okay, so is this limit cycle found stable? You have to check eigenvalues of Jacobian numerically.